Hello and welcome to this introductory video about ChimeraX. ChimeraX is a software tool that we are going to use as the main tool for making different molecular modeling and visualization, analysis operations. It's a software that was developed by the University of California in San Francisco just a few years ago, and it replaced its predecessor, UCSF Chimera, and it has some additional functionalities comparing to its predecessor. So let's look closer at this software and learn how to do basic things, basic manipulations and operations in ChimeraX. When you open the ChimeraX, you see the screen like this, but most likely you will have here in the main part of the window only a gray screen because it lists the recently opened files, but you don't have any of them. So you will have only a gray screen here. And let's load our first file. For this, we will use one of the examples from Protein Data Bank. And I suggest you to use this one, this record. So if you see this command prompt, if you look at the bottom of the screen, there is a console or command prompt where you can write different commands. And first command that we are going to learn is the command open. This command allows you to download files directly from different databases like Protein Data Bank, AlphaFold database, databases of electronic density maps, and so on. So by default, if you write open and then four-letter code, like this one, 4ERY, you will download a file from Protein Data Bank. So here is the adenosine A2A receptor of human origin, and we will use it as the test example. So which parts of the screen, which toolbars and elements of interface do we have here in ChimeraX? First, if you look at the main part of the screen, the largest part is occupied by 3D model. So it's a graphical or 3D view window. Here we can do all the manipulations with molecules like rotation, translation, zooming, scaling, and so on. By default, if you press and move the left mouse button, you will rotate the molecule. If you press and move the right mouse button, you will move it. So do translation. And if you move the middle mouse button wheel, you will do scaling up and scaling down. So it's zooming. If you press and hold the middle mouse button, you will also make translation moves. So it's very easy. Here to the right, we have additional vertical menu with two basic parts. One of them is log, it's above, and then below we have a model panel. Log is the place where you can read different outputs and additional information about the files that you have here. So let's try doing this. Here you see that after we executed the open command, then this file was downloaded from Protein Data Bank. And here we see the basic information about this record. So it has only one chain A, then name of this file. Here it's not correct because it's too small. So actually it's adenosine A2A receptor in complex with cytochrome, but for some reason it's not large enough to show everything. Yeah, now it's correct. So if you press more information, you can see the whole name. So it's adenosine A2A receptor, A2A in complex with cytochrome. And here you have the UniProt ID, and it's very convenient to go directly to a UniProt record that corresponds to this Protein Data Bank file. Then you can see the list of non-standard residues. It means non-amino acid residues like ligands, SZMA, and different solvents, ions, different molecules that were added during crystallography phase, for example. And also one suitable option, if you press here, you can select the chain or the ligand. So if you press A, you will see that part of the chain that corresponds to the adenosine A2A receptor chain A is highlighted in green. So in Chimera, each time you select something, it is highlighted with the green frame. So the easy conclusion from this selection is that this part, which is not highlighted, is those parts that belong to cytochrome B562, which was used as a co-crystallographic molecule here. The same way, if you press names of different molecules here, you will highlight them. Here, as you can see, with this green frame, now we can see the ligand, for example. But there is more convenient way how to move the camera view on the molecule of interest. For this, we can use either command or toolbar, and it's one of the strong sides of ChimeraX that you can do the same operations in multiple different ways. So usually in Chimera, you have 3 or 4 options how to do the same. You can write the command in the command prompt in the bottom part of the window. You can use the toolbar, or you can do some commands directly from the graphical window, or you can also use the context menu. But most manipulations are done using commands and toolbar. So if you go to toolbar in graphics here, in the section camera, we have different options. If you press use selected, the screen will be focused on the selected molecule. So here, if we now select the sodium ion and use selected, we will move to it. If you want to go back, then you can press view all, and you will see the whole molecule. Here you can also, using this toolbar, you can also make some basic modifications on the graphical window, on the representation. For example, you can make white or gray background or go back to black. So let's make it black. And here you can also optimize the graphical representation, so change visualization a bit. You can add silhouettes, so it will look more fancy. You can change the light. It's by default simple light, or you can make a soft light, cool light, or flat, which looks more or less as a cartoon. So let's go back and use simple visualization. There are also options to modify view, focus camera on selection or on the whole molecule. So you can orient the molecule by axis, or you can change the side view. So here is the additional window, and by moving this line, you can clip the molecule. So as you see here in the bottom right part of the screen, you have the side view window, and if you move this line, you're clipping the molecule. So for example, now if you again select the ligand, focus the screen on it, you will see that here in the side view, everything changed. So now if you move back, you will see that you don't have the whole molecule, it's clipped. But if you change it here, you will have again the whole molecule. But you can always press view all. The same can be done with the command view. For example, if you zoom it and then write and execute command view, it will do the same. So let's check what else can be done using ChimeraX. Now let's look closer at different toolbars that we have. So first of all, we have a menu line. File is for opening and saving files, and also closing session and quitting from Chimera. Then edit is only for undoing and redoing, but beware of using these options because in molecular modeling software, unfortunately, in almost any software, you cannot do the proper undo. So try to do everything from the first time. Then we have select, and this menu allows you to make different kinds of selections. For example, you can select specific chain of your molecule. You can select specific types of chemicals. For example, specific chemical element like oxygen or phosphate, specific functional group, or you can select only nucleic acids or proteins. Then you can specify which residue to select, which kind of amino acid or not amino acid, residue small organic molecules. Then you can select specific structure like solvent or ions or protein or backbone or the secondary. structure elements. It's very convenient. Then here you can indicate specific sequence that you want to select. Specific zone, for example, you can select only zone within local environment of ligand of interest. You can select specific contacts. As well, you can clear selection. So again, you see that there are multiple ways of doing the same things. For example, if you selected something and you want to clear the selection, you have at least 3 options. You can write the command, select clear. Then you can press left mouse button and control on the empty part of screen. And then you can go to menu select and press clear. If you want to invert selection, for example, if you selected ligand first and then you want to select everything except ligand, you can invert selection. Then you can select everything, broaden or narrowing the selection. It can also be done with arrow keys, up and down. If you want to expand selection, you press up arrow key. If you want to narrow it, you press down key. Let's check how it works. So, for example, here we select one of the residues. If you hover mouse, you see that it's isobutene 127 from chain A. So you can select it by pressing left mouse button and control. And then if you press up, you will select the whole helix. And if you keep pressing up, you will select the whole domain. And if the protein has more domains, you have to press one more time to select the whole protein. And if you keep pressing, you will select everything that you have here. And the same way, if you press down, you will narrow the selection up to your initial selection. So it's very, very convenient. Then we have actions menu. This menu allows you to hide or show atoms, to hide and show secondary structure, which is called cartoon. Then you can hide or visualize surface and change the type of surface. You can color the selection, then add labels, and change the screen view by pressing U. And also, if you have selection, you can set pilots and inspection. But we will look at this closer at the next modules. So now let's try coloring some parts of the protein. Let's see how to do it. The easiest way, if you want to color one of the helixes, for example, this helix, so you select it, press up until you select the whole helix, and then go to Actions, Color, and select color, for example, blue. Then you can clear the selection, select, clear. Yeah. Otherwise, you can also use the molecule display here to change the types of representation. For example, let's hide all atoms that we have. So if you press hide in section atoms, you will hide all atoms. Now, if you press show, you will show all atoms. So each amino acid and each non-standard residue. So let's hide them at the moment. Then here, cartoon section, if you press hide, you will hide everything. Then show, you will have your secondary structure elements back. So for example, now we can show atoms and hide secondary structure. So this is atomistic representation of your protein. Then we can also show surface, which represents molecular surface. So it's more or less realistic visualization of the protein volume. Of course, in real nature, in real cells, proteins do not have any colors because their size is much smaller than the size of light wave. But in molecular modeling, we can easily assign them different colors. Then when you have surface, you can edit, of course, or you can show it back. And now you can change the type of surface. Here in the coloring sections, you can show electrostatic surface, so it will calculate the Coulombic potentials. So here we have the surface of protein colored by electrostatic potential. Blue color responds to positively charged residues like arginine or lysine or histidine. Red color responds to negatively charged residues like glutamate and aspartate. and white color is the neutral residues. The darker the color is, the higher the charge is. So this white-red color, for example, means that here we have low negative potential. So it's very easy to do. Let's focus our screen again. Then you can use hydrophobic representation instead of electrostatic. So press hydrophobic, and now you have the surface of protein rendered according to the hydrophobic or hydrophilic properties of molecules. Here, yellow color, this brownish color corresponds to lipophilic parts of protein, and this cyan or pale green color corresponds to hydrophilic. And you can see that these oleinic acid residues that we have, they are adjusted exactly in the places where we have lipophilic parts of proteins. Since we know that it's a G-protein coupled receptor, which is a transmembrane receptor with 7 transmembrane helices, of course, we are expecting to have this kind of hydrophobic transmembrane part. And we see really that most of the hydrophobic residues are located in this part, which interacts with the membrane. Then you can also color the protein according to B factor. B factor is a temperature factor, so it corresponds to the flexibility and to the reliability of resolution. So if you have dark blue color, it means that positions of the atoms are very fixed, very clearly resolved. And if you have red color, it means that these atoms were moving, so there were less electronic density, or there were alternative conformations of these functional groups. So we can say that flexibility and movement of these groups are higher comparing to this blue part. Okay, so now let's hide the surface and let's color the whole protein. So if you do not select anything, by default, the action will apply to the whole protein. So I'll go to Action, Color. Let's make the whole protein gray, dark gray. Let's hide the atoms and show the carbon. Okay. So here we have our helical structure of adenosine A receptor. And we can now visualize the ligand. So for this, you can address it by naming its ligand. So for example, you can go to Select, Structure, Ligand. And now you can press Show, it will show only selected atoms. So since here we have many non-standard residues, not only your ligand, but also residues of fatty acids were selected. So to make the selection more specific, more precise, you have to address the ligand by its name. So go to Select, Residues, and select ZMA, because this ligand is the inhibitor called ZMA, and there are some digits after it. Okay, so now we have our ligand selected. So let's zoom into it. So select, Actions, View. We have now our ligand centered on the screen, and let's color it. So go to Actions, Color, and let's make it lion. And it's very important to have a standard coloring. It means that you can have any color for carbon atoms that you like, but you have to keep the standard coloring for hydrogen, which is white, oxygen, which is red, nitrogen, which is blue, sulfur is yellow, and phosphate usually is like orange. So go to Actions, Color, by heteroatom. It's very important to keep this commonly accepted coloring, because if you will publish it, then anyone will require it for you, because it's a commonly accepted standard way of coloring atoms. Okay, so now let's visualize the local environment of this ligand. For this, select it again, so you can go to Select, Residues, ZMA, or you can press the Control and left mouse button on it. It doesn't matter. Then go to Select and Zone. Here, select residues that lie within 5 angstroms from the currently selected atoms and press OK. So as you can see, some parts of protein were selected now, and then press Show. Okay, so you see all the atoms shown as sticks, which reside within 5 angstroms from your ligand. They compose the local environment of ligand. And again, let's color them by heteroatom. Yes. So you see that there are many water molecules around your atom, and maybe they even involved in hydrogen bonding. We don't know it yet, but we can show it later. And also we have some residues. Now let's label the residues. So go to Actions, Label, Residues, and put the name and number. Okay, so now you see that here is your ligand ZMA, then we have some of the residues, and also H2O, so water solvent. Of course, you can also easily remove the excessive labels that you don't like. For example, now let's select the solvent, select Structure, Solvent, and then go to Actions, Label, Residues, Off. Okay, so now we have labels only for the ligand and for the amino acid residues that reside within 5 angstroms of your protein. So here we want to optimize, for example, the view, because currently our ligand is covered with the alpha helices. So we can go here, to the right part of the screen, side view, and move these lines a bit and adjust the view. So by moving it, we can remove everything that covers your ligand. So now it's slightly better. And to make picture look less crowded, you can also move this right part. So now it's much less crowded. You can play in your free time. Yeah. And finally, we're gonna visualize the H bonds and non-hydrophilic contacts using ChimeraX graphical user interface. The easiest way to do it is to use this part, which is called Analysis section on the toolbar, or alternatively, you can go to Menu, Tools, Structural Analysis, and select H bonds or contacts. So let's start with H bonds. Imagine that we are interested in knowing which kinds of interactions are there between the ligand and the protein. So again, let's select the ligand. Now click here on H bonds, and automatically you have all H bonds related to this ligand. So let's play a bit with visualization to show all of them. So you see that there are many H bonds, and if you look at the log, you will see that 10 hydrogen bonds found. But it's a very rough way to do it. So let's hide the H bonds, press this button, and let's make it in a more sophisticated way. So select again ligand, residue ZMA, go to Tools, Structural Analysis, H bonds. Here you have a menu that allows you to modify some options. If you want to be sure that H bonds that will be visualized involve ligand, which we want to know, you have to limit the selection here. So this option with at least one end selected guarantees that all H bonds will involve the selection, in this case, ligand. Then this option, Reveal Atoms of H bonding residues, has also to be activated, and this write information to log. In my case, I have previously activated all these functions, but in your case, if you start Chimera and use it for the first time, you have to do it by yourself. Okay. So we have the same result, but in this case, in the log, we have the full list of H bonds that we have. So you can see which atoms and functional groups are involved in the formation of these H bonds. For example, the first H bond involves the nitrogen atom from asparagine 253 and nitrogen atom of ZNA ligand. And you can also see here the distance between donor and acceptor. And according to criteria that you again manually modify, you can have different number of hydrogen bonds. Because you know from literature that hydrogen bonds can exist in some distance range. Okay, so again, let's hide hydrogen bonds, and now let's look closer at the contacts. So go to Tools, Structure Analysis, Contacts. So it will show you the hydrophobic interactions and van der Waals interactions. Okay, so let's activate display as cytobonds. Let's write information to the block. And other parameters can be left by default, but be sure that reveal atoms of interacting residues also activated. Otherwise, you won't see all the atoms that are involved in these interactions. So now press OK. So these green dashed lines are all possible van der Waals and hydrophobic interactions, like E-stacking, PP interactions, dipole interactions, and so on, that can be established between your ligand and its environment. So also between ligand and solvent, and between ligand and protein. So we don't really need to show all of them. It's enough just to look at the log. So here we have 66 contacts. Again, we know which atoms are involved in these contacts. And now we can hide them. So for this, we can go back to structure analysis, contacts, show them again. But this time, do not display pseudobonds. Okay, so now let's look closer to the model panel, and it will be the final part of this introductory tutorial, because it will be enough for you to start. In the model panel, you have a few options. So here you see the name of your protein. It has ID 1, and then it has different additional things, additional objects that you can manipulate one by one. Example, labels. So when you create labels, they immediately appear in the model panel. You can show them or hide them easily. And you can remove them by clicking Close. Then we have the surface, which is we had before, but now it's not shown. So we can remove all this unnecessary stuff here and remove all the bonds. So again, for example, if you created the hydrogen bonds, if you visualized them before, they will also appear here and you can manipulate them. So for example, if you want to hide them, just find this part, hydrogen bonds, and press on this icon and hide them. You can also select them. For example, if you want to modify the representation. The same way, if you had visualized contacts before, let's make it again, and you want to get rid of them, then you can select these contacts and close them. So it's a very easy and handy way of manipulating molecules. Okay, so it should be enough for you to start. I hope you enjoyed this tutorial. And of course, if you have any questions or any troubles, problems with ChimeraX, please do not hesitate to write on the forum. You can use any of them, and I will try to reply as soon as possible. So now you can move to the exercise. Enjoy, and see you later.